let's make a spell checker. If you open speller.c, then you'll see that most of the functionality for checking a text file against a dictionary is already made for you. /speller, passing in a dictionary text file and then another text file, will check that text file against the dictionary. Now, dictionary text files will contain valid words, one per line. Then speller.c will call load on the dictionary text file. It'll call a function called check on every word in the inputted text file, printing all misspelled words. Speller.c will also call size to determine the number of words in the dictionary and call unload to free up memory. Speller.c will also keep track of how much time is used to conduct these processes, but we'll get to that later. So what do we need to do? We need to fill in dictionary.c. In dictionary.c, we have the helper function load, which loads the dictionary, the function check, which checks if a given word is in the dictionary. The function size returns the number of words in the dictionary. And finally, we have unload, which frees the dictionary from memory. So first, let's tackle load. For each word in the dictionary text file, load will store those words in the dictionary data structure of your choosing, either a hash table or a trie. I'll go over both in this walkthrough. First, let's talk about hash tables. Say you had 10 billiard balls and you wanted to store them. You might put them all in a bucket, and when you needed a specific numbered ball, you'd take one out of the bucket at a time, looking for that ball. And with only 10 balls, you should be able to find your ball in a reasonable amount of time. But what if you had 20 balls? It might take a little longer now. What about 100? 1,000? Now it would be much easier if you had multiple buckets, maybe one bucket for balls numbered 0 through 9, another bucket for balls numbered 10 through 19, and so on. Now when you needed to look for a specific ball, you could automatically go to one specific bucket and search through that bucket. And if each bucket has approximately 10 balls, then you could easily search through it. Now, since we're dealing with dictionaries, one single bucket for all of the words in the dictionary will probably be far too few buckets. So let's take a look at hash tables. Think of it as an array of buckets, and in this case, the buckets are our linked lists. And we'll distribute all of our words amongst these multiple linked lists in an organized way, using a hash function, which will tell us which bucket a given key, a given word, belongs to. Let's represent this schematically. The blue boxes here contain values, and red boxes point to another value pointer pair. We'll call these pairs nodes. Now, each bucket, as I said earlier, is a linked list. In linked lists, each node has a value as well as a pointer to the next value. Now, dealing with linked lists, it's very important that you don't lose any links. And another fact to remember is that the last node, if it doesn't point to another node, points to null. So how do we represent this in C? We define our struct here, and the value in this case is a char array of length plus 1, where length is the maximum length of any word, plus 1 for the null terminator. And then we have a pointer to another node called next. So let's make a small linked list. First, you'll want to malloc your node, which creates space in memory the size of your node type. And make another node, again mallocing. Now if you want to assign a value to a word, then we might say node1 arrow word equals hello. This arrow operator dereferences the pointer and accesses the struct's variables. This way we don't have to use both the dot and the star operator. So then I have node2 arrow word equals world. And there the values are populated in my nodes. To make the links, I'll pass in node1 arrow next, accessing that node star, that node pointer, equals node2, pointing node1 to node2. And there we have a linked list. So that was just one linked list, but a hash table is a whole array of linked lists. Well, we'll have the same node structure as before, but if we wanted an actual hash table, then we can just make a node pointer array here, for example, size 500. Now notice, there's going to be a trade-off. between the size of your hash table and the size of your linked list. If you have a really high number of buckets, imagining having to run back and forth in a line to find your bucket. But you also don't want a small number of buckets, because then we're back to the original problem of having too many balls in our bucket. Okay, but where does our ball go? Well, we first need to have a ball, right? So let's malloc a node for every new word that we have. Node star, new node, equals malloc size of node. Now that we have this structure, we can scan in, using the function fscanf, a string from our file, if that's a dictionary file, into new node arrow word, where new node arrow word is our destination of that word. Next, we'll want to hash that word using a hash function. A hash function takes a string and returns an index. In this case, the index has to be less than the number of buckets that you have. Now, hash functions, when you're trying to find one and create one of your own, remember that they have to be deterministic. That means that the same value needs to map to the same bucket every time that you hash it. It's kind of like a library. When you take a book, based on the author, you know which shelf it should go on, whether it's shelf number 1, 2, or 3. And that book will always belong in either shelf 1, 2, or 3. So, if new node arrow word has the word from your dictionary, then hashing new node arrow word will give us the index of the bucket of the hash table, and then we'll insert that into that specific linked list indicated by the return value of our hash function. Let's look at an example of inserting a node into the beginning of a linked list. If head is a node pointer that indicates the beginning of a linked list, and new node indicates the new node that you want to enter in, just assigning head to new node would lose the link to the rest of the list. So we don't want to do this. Rather, we want to make sure that we hold on to every single node in our program. So running new node arrow next equals head, and then head equals new node will preserve all of the links and not lose any. But what if you want your list to be sorted? Because having a sorted linked list might be easier for searching in it later on. Well, for that, you'll need to know how to traverse linked lists. To traverse a linked list, let's have a node pointer, a node star, to act as your cursor, indicating which node you're at, starting at the first element. Looping until cursor is null, we can conduct certain processes and then advance the cursor when we need, using cursor arrow value. Remember, this is the same thing as saying star cursor, dereferencing cursor, then using the dot operator value. So updating the cursor is by assigning the cursor to cursor arrow next. Say you determine that D becomes in between C and E. To insert the node, have the new node D point to the node E, which is cursor next. And then C, the cursor, can then point to D. That way you maintain a list. Be careful not to lose your links by moving cursor arrow next to D right away. All right, so that's how you might insert nodes, load words into those nodes, and insert them into your hash table. So now let's look at tries. In a try, every node will contain an array of node pointers, one for every letter in the alphabet plus an apostrophe. And each element in the array will point to another node. If that node is null, then that letter isn't going to be the next letter of any word in a sequence. So, because every word indicates whether it's the last character of a word or not. Let's look at a diagram. Hopefully things will be a bit clearer. In this diagram, we see that only certain letters and certain substrings are being listed out. So you can follow certain paths, and all of those paths will lead you to different words. So how do we represent this in C? Well, every node now is going to have a Boolean value indicating whether that node is the end of a given word or not. And then it'll also have an array of node pointers called children, and there are going to be 27 of them. And remember, you'll also want to keep track of your first node. We're going to call that root. So that's the structure of a try. How do we represent this as a dictionary? Well, To load words in, for every dictionary word, you're going to want to iterate through the try. And each element in the children corresponds to a different letter. So, checking the value at children index I, where I represents the specific index of the letter that you're trying to insert, well, if it's null, then you'll want to malloc a new node and have children I point to that node. If it's not null, then that means that that given branch, that given substring already exists. So then you'll just move to that new node and continue. If you're at the end of the word that you're trying to load in the dictionary, then you can set that current node that you're on to true. So let's look at an example of inserting the word fox into our dictionary. Pretend we start with an empty dictionary. The first letter F will be located in children index 5 of the roots children array. So we insert that in. The letter O will then be in children index 15 after that F. And then X will be even below that, branching off of the O's children. And then because X is the last letter of the word fox, then I'm going to color that green to indicate that it's the end of the word. In C, that would be setting the isWord boolean to the value true. Now, what if the next word that you're loading in is the word foo? Well, you don't need to malloc any more space for F or for O because those already exist. But the last O in foo, that one you'll have to malloc, make a new node for that, setting the isWord boolean to true. So now let's insert dog. Dog will start with index 3 of the roots children because D hasn't been created yet. And we'll follow a similar process as before, creating the substring dog, where the G is colored green because that's the end of a word. Now, what if we want to insert do? Well, this is a substring of dog, so we don't need to malloc anymore, but we do need to indicate where we've reached the end of that word. So the O will be colored green. Continuing that process for every single word in your dictionary, you've loaded them into either your hash table or your try. Speller.c will pass in strings for dictionary.c to check them. Now, the check function has to operate under case insensitivity. That means that capital letters and lowercase letters and a mix of both should all equate to true if any combination of that is in the dictionary. You can also assume that strings are only going to contain alphabetical characters or apostrophes. So let's look at how you might check with a hash table structure. Well, if the word exists, then it can be found in the hash table. So then you can try to find that word in the relevant bucket. So which bucket would that word be in? Well, you'd get the number, that index of the bucket, by hashing that word, and then searching in that linked list, traversing through the entire linked list using the string compare function. If the end of the linked list is reached, meaning that your cursor reaches null, then the word is not to be found in the dictionary. It won't be in any other bucket. So here you might see how there might be a trade-off between having either sorted linked lists or unsorted ones. Either will take more time during load or more time during check. How might you check in a try structure? We're going to travel downwards in the try. For each letter in the inputted word that we're checking, we'll go to that corresponding element in the children. If that element is null, then that means that there are no substrings containing our input word, so the word is misspelled. If it's not null, we can move to the next letter of the word that we're checking and continue this process until we reach the end of the input word. And then we can check if isWord is true. If it is, then great, the word's correct. But if not, even though that substring exists in the try, the word is misspelled. When the function size is called, size should return the number of words that are in your given dictionary data structure. So, if you're using a hash table, you can either go through every single linked list in every single bucket, counting the number of words are there. If you're using a try, you can go through every non-null path in your try. Or, while you're loading the dictionary in, maybe you can keep track of how many words you're loading in. Once Speller.c finishes checking the text file against the dictionary, then it's done, and so it calls unload, where Your job is to free anything that you've mallocked. So if you use a hash table, then you need to be especially careful to avoid memory leaks by not freeing anything prematurely and holding on to every single link before you free. So for every element in the hash table and for every node in the linked list, you'll want to free that node. How do you go about freeing a linked list? Setting your node pointer cursor to the head, to the beginning of the linked list. Then, while your cursor isn't null, you can set a temporary node pointer to your cursor. Then advance the cursor, and then you can free that temporary value while still holding on to everything afterwards. What if you're using a trie? Then the best way to do this is to unload from the very bottom to the top. By traveling to the lowest possible node, you can free all pointers in that children, and then backtrack upwards, freeing all elements in all of the children arrays until you hit your top root node. Here's where recursion will come in handy. To make sure that you've properly freed everything that you've mallocked, you can use Valgrind. Running Valgrind will run your program, counting how many bytes of memory you're using and making sure that you've freed them all, telling you where you might have forgotten to free. So run that, and once Valgrind tells you and gives you the go-ahead, then you've finished unload. Now, a couple of tips before you go off and start implementing your dictionary. I'd recommend to pass in a smaller dictionary when you're trying to test things out and debugging with GDB. The usage of Speller is /speller, an optional dictionary, and then a text. By default, it loads in the large dictionary, so you might want to pass in the small dictionary or maybe even make your own, customizing your dictionary and your text file. And then finally, I'd also recommend to take a pen and paper and draw things out before, during, and after you've written all of your code to just make sure that you've got those pointers just right. I wish you the best of luck. And once you've finished, if you'd like to challenge the big board and see how fast your program is compared to your classmates, then I encourage you to check that out. With that, you've finished the Speller P-Set. My name is Zamila, and this is CS50.